Quicksort can feel almost magical. It sorts by repeatedly drawing one line through the data, smaller values on the left, larger or equal values on the right, depending on the equality rule. But the whole strategy depends on one fragile choice. If the pivot keeps landing in the wrong place, the magic collapses into a long, expensive chain. In this video, you will learn what partitioning actually does, why the pivot controls Quicksort's shape, how a bad pivot creates the worst case, and why randomness is not chaos here. It is a defense mechanism that makes predictable disasters much harder to force. The core operation is partition. Pick a pivot value. Scan the array. Every item smaller than the pivot moves to one side. Larger or equal items follow the equality rule used by that partition scheme. In this visual version, the pivot lands in its final sorted position. Other partition schemes may return a boundary instead, but the same split idea drives the recursion. Important caveat: if there are many equal keys, a simple two-way split can waste work, so production quicksorts often use three-way partitioning or duplicate guards. Here is the move in slow motion. We do not compare every item with every other item. We compare each item to the pivot and send it through one of two gates. This single pass is why each partition level costs about n work, even before the recursive calls begin. During partition, the algorithm protects a simple promise, formally called an invariant. Everything already placed on the left is less than the pivot. Everything already placed on the right follows the greater or equal side of the rule. The middle is the unknown scan zone. As the scan moves, the unknown zone shrinks, but the promise stays true. Think of the pivot as a temporary wall. It does not solve the whole problem, but it separates the problem into two rooms. Nothing on the left needs to cross to the right later, and nothing on the right belongs on the left. That is the source of Quicksort's power. When the pivot lands near the middle, the two rooms are roughly balanced. The recursion tree stays shallow. Each level still touches most of the items once, but there are only about log n levels. That is the healthy n log n shape we want. The easiest way to feel n log n is to count work by levels. At the top, partition touches n items. One level lower, the two partitions together still touch about n items. If balanced splitting gives about log n levels, the total becomes n times log n. When the pivot is always the smallest or largest item, one room is empty and the other room contains almost everything. Quicksort is no longer splitting the problem in half. It is peeling off one item at a time. That creates the quadratic worst case. The same partition code can create two very different cost shapes. Balanced pivots give many short levels. Extreme pivots give a long staircase. This is a beautiful algorithm lesson. Performance is not only about what each step does. It is also about the structure those steps create. A simple implementation that always chooses the first item as pivot can be tricked by already sorted input. The input looks friendly to a human, but to that pivot rule it is a trap. Every pivot is extreme, so the recursion becomes a chain. Randomized quicksort changes the game. Instead of letting a fixed input order determine the pivot pattern, we choose a random pivot, or shuffle the input before sorting. Now a malicious or unlucky ordering cannot reliably force the same bad sequence of pivots. There are two common ways to get the same protection. One is to shuffle the array once and then use an ordinary pivot rule. The other is to choose a random pivot inside each subarray. Either way, the important point is that pivot order comes from the algorithm's random choices, not from the input order. Randomness does not need to find the exact median. Quicksort only needs enough decent pivots. If a pivot lands somewhere in the broad middle, the split is useful. A 70-30 split is not perfect, but it still shrinks both sides. A 90-10 split is worse, but even that is not fatal once or twice. The danger is repeating extreme splits level after level. A few imperfect splits are fine, because the tree can absorb them without becoming a staircase. This is why we say randomized quicksort has good expected running time. Expected does not mean every run is identical, and it does not mean the algorithm has forgotten its worst case. It means that over the random choices, the average behavior is strong. The worst case n squared still exists, but randomization makes it unlikely instead of predictable. That protection assumes the pivot choice is private enough and random enough. If an attacker can predict the random generator or pivot rule, they may still shape bad inputs. In practice, the goal is not to prove bad luck impossible. It is to make bad luck too rare to plan around for ordinary inputs. A single bad pivot is not the disaster. The disaster is a long streak of bad pivots on many recursive levels. Randomization makes that streak unlikely. Most pivots will be somewhere useful, some will be mediocre, and a few will be bad. The tree does not need perfection, it needs enough good splits spread through the run. That is the practical meaning of expected n log n. Quicksort is often fast in real systems because partitioning scans arrays in a local, machine-friendly way. It tends to touch nearby memory, has small constant factors, and usually uses little extra space beyond the recursion stack. That stack is expected O of log n with good pivots, but it can grow to O of n if the split keeps failing. Big O explains the shape. The hardware explains some of the speed. There are many pivot rules. First item is simple but fragile. Random pivot is robust against input order. Median of 3 samples a few candidates and chooses a middle-looking one. The rule is not decoration. It is a steering wheel for the recursion tree. Many equal keys can also hurt basic quicksort. If half the array has the same value, splitting into only less and greater can waste work. Three-way partitioning fixes this by creating a middle zone, less than pivot, equal to pivot, and greater than pivot. The deeper idea is not just about sorting. Randomization can remove power from an adversary. If the algorithm makes a private random choice, the input designer cannot know exactly where the algorithm will step. Randomness becomes controlled uncertainty. Quicksort is not always the best choice. If you need guaranteed worst-case time, heap sort or merge sort may be safer. If you need stability, basic quicksort is not stable. If your keys are small integers, counting or radix sort may use stronger assumptions and win. Production sorting code usually adds guardrails. Small subarrays may switch to insertion sort because the overhead of recursion is not worth it for tiny pieces. Recursion depth may be limited so a suspiciously tall chain is noticed early. Some systems use introsort, which begins like quicksort but falls back to heap sort if the recursion gets too deep. The elegant idea becomes safer through engineering: use quicksort when the shape is healthy, and switch tools when the shape starts looking dangerous. Before using quicksort, ask 4 questions. How will the pivot be chosen? Are there many duplicate keys? Is worst-case behavior dangerous? Does the implementation protect small arrays and recursion depth? These questions turn quicksort from folklore into engineering. Here is the mental model. Quicksort is partition plus recursion. The pivot controls the shape. Balanced splits lead to n log n behavior. Extreme splits lead to n squared behavior. Randomness helps because it makes bad pivot patterns hard to predict and hard to force. In the next video, we move from algorithms to the things they manipulate, data structures. We will see why arrays, lists, stacks, queues, heaps, trees, and hash tables are not just storage containers. They are ways to prepay time for future operations.